Okay, we're recording. Cool. So you should update your curriculum with Git pull if you haven't. Mine is naturally already up to date. You'll see day 3, we have some stuff in there like this big O demo, which I'm not sure I will run ever. We can try it, but Big O MD has a bunch of content we cover. But also at the top here are these Big O slides. So that's what I'm looking at right here. And the goal of today's lecture is really just to spend even more time talking about Big O. So we introduced Big O a little earlier than we normally do, just to give you a little taste for it, because as you probably could have told, it doesn't really make sense to talk about data structures and algorithms without Big O. They all go together because data structures are the way you're shaping the data, and algorithms are what you're trying to accomplish given the shape of the data. And Big O is what tells you, is that the shape you want for the thing you're trying to accomplish? And so they do all go together, but now we're going to talk about it a little more explicitly. Okay. So Big O essentially is about this idea of how your algorithm is affected by change in the size of an input. So when we say an algorithm's performance, there's a couple ways we could think about that. We could think about that in terms of time. How long does it take to run, right? That's a pretty natural way to think about performance, but the problem with that approach is that if I buy a computer today, or let's say I bought a computer, 10 years ago, a certain algorithm might have taken, 10 minutes to run. And now it takes 1 minute to run because technology has improved. My algorithm has not improved. My physical hardware improved. The algorithm is identical. So how do we measure the algorithm's performance in a way that is hardware agnostic? Because many, many algorithms, were not necessarily able to run in any kind of efficient time in like the 1940s. Whereas the inverse is also true. You can write something really, really inefficient now, but if your computer is powerful enough, it's going to be able to run it. And that opens or closes different doors based on, what the current reality is. But we're trying to think of this stuff outside of time, outside of technology. We're actually saying like, this is an algorithm. It's just an idea on paper. How do we compare one algorithm to another? And the way we do that is we measure it in, approximately steps that it takes, a number of individual steps it has to take to accomplish its goal. And we do that relative to the size of the input. So yeah, mentioned here, we could care about execution speed. That's essentially what this slide is trying to say is that, we don't really think of it in terms of speed, but yeah, you care about number of commands, and that's what we call time complexity. But there's actually this other thing which we haven't really discussed much, which is called space complexity. And that's that other thing in LeetCode where it says like, how did you perform versus everyone else in terms of time, but also how did you perform versus everyone else in terms of memory usage, because actually how much resources you use could matter too. So maybe if I'm going to open like ExcaliDraw for a second, you might have seen something where there's like, some algorithm. Let me get something like this. Maybe you have some algorithm in which you're asked to like reverse this array, right? And so one way you could do it is what we call in place. And what that means is that we're going to do some kind of swapping like this. So we're going to swap the first and the last. We're going to swap these. We're going to swap these. And then we're done. We did an in-place reverse of this list. call this input. So we took the input, we actually mutated it, and then that's what we returned as the output. So in most languages, if you see, like if I'm going to open up Python for a second here, if I were to say, you know, array equal, or, you know, because it's Python, I might as well call it list equals 1, 2, 3, 4, 5. And then I say list dot reverse. What actually happens, you'll see it takes no input. Okay. And then what happened? It didn't return me any output. Why not? Because if I type list now, what that actually did was take that list that it was referring to, and this method on the list mutates the list in place. But you could think of another approach where maybe dot reverse, it still takes no input, but it returns output without changing the original. So if I put this back in order, again, I'm going to call this input. Maybe what I do is that I actually create a brand new list called output, and that's what I'm going to return. And that's the one that I actually do the reverse on. And this is, you know, a different approach that's not better or worse fundamentally, in that it's going to preserve that original one. I didn't reverse the original. I took the original, I used it as input to create this new thing called output, which is the reverse list. And now whoever called this function has a reversed version of the list. And in terms of time complexity, that swapping algorithm is exactly the same. So it's no different in terms of time complexity. But in terms of resources, well, in this case, in the first case, because I swapped it in place, I didn't create any new resources. Maybe I created some variables, but that's an example of constant time space. I'm not creating anything new, or if I am, I'm creating something new that's not in relation to the size of the input. Whereas in this case, if this input is 5 elements or 6 elements, I'm creating a new list of 6 elements. If this input was 1 billion elements, I have to create a new list of 1 billion elements in order to run this. And so that's what the resource optimization space complexity thing is. Sometimes you are creating new memory that is related to the size of the input, just in the same way that, you know, time-wise, something can be related to the size. And so that's something to consider. And when you're analyzing an algorithm, it's generally like you want to provide both the time and the space complexity. The caveat to that is that people care way more about time versus space complexity, because computers are faster than they once were, but not to the point that time doesn't really matter. Whereas we're at the point with computers now where even if something takes up a massive, massive amount of space, it really doesn't matter. You can find the space for it. We're not really limited to space. The fact that I can buy a Nintendo DS like micro SD cartridge that's this big, that has 256 gigabytes on it, and it cost me like 20 bucks, that tells you space is not the big concern. Whereas if you have an algorithm in a video game and, you know, because of how you wrote it, it's a little inefficient. So instead of being able to do 60 frames a second, we can only manage like 30 frames a second. The user is definitely going to notice that. So time is very much, it probably always was more important than space complexity, but in the modern day, it's barely really a concern, space, because you can just get on Amazon, on AWS, and, you know, suddenly you have access to what they S3 is their like bucket. You pay like cents to just have a ton of space, and it's a bucket. You just put things in the bucket. Okay. Big O notation. We've covered some of this, but just how we read this, the big O in there means worst case scenario. There actually are things other than the big O. We can look at them if you're curious. People don't tend to talk about them a lot, but there's big theta, and there's little o, and there's these other things that represent things other than worst case scenario. They represent average case scenario or best case scenario. That's kind of useful when you're trying to give like a full rundown of how some data structure works or algorithm works. You're saying, oh, well, actually, there is this best case. So just know about that. Or you could say, well, we do have this average case. That gets a little more complicated what average actually means. But people tend to care about worst case because if you're trying to sort a list, that list might come to you in reverse order. And your algorithm is probably designed such that that's the hardest case for it to solve, that it has to do the most work. And we just want to know what the most work is because that sort of sets a limit. It can't get worse than this. Size of an input, right. So that n, lowercase n, capital N, it doesn't matter. It's there to represent the size of the input. So that size might be an array. It might be a tree. It can really be anything. It's just about what is the part of it that can grow, or what's the part of it that when it grows, it affects performance. So if you're trying to search through an array, the size of the array is going to matter because you're going to have to look at each element. But by the same token, let's say we're trying to compute the Fibonacci number. If you're trying to compute the, there's no input there that's like an array or a tree, or it's not a complex object of any kind. But if you're trying to compute the 20th Fibonacci number versus the 50th Fibonacci number, there's going to be a big difference based on the size of that input, the number you're looking for. So n can also just be a number. It really matters what the nature of the problem is. And so people will often be sort of, you're using n in this general sense, but it really just refers to the thing in the problem that can grow, that grows fastest in like, a theoretical world of figuring out a hard version of that problem. Okay, so here's some common complexity cases. We've covered some of these already. I just wanted you to see all of them before we go in more depth. This is constant time. This is the best possible you can get. It's just looking something up in an array, like indexing in an array. Constant doesn't mean it's exactly one operation. It could be exactly 10 operations. It could be exactly 1,000 operations. It just means that it doesn't care about the input size. Whatever the input size is, it's always going to be exactly the same. I see Chris raised his hand, but he's muted.
Sorry. I just had a question. Like behind the hood, when we look at the length, does it automatically does it index it? Like it just goes to the length, or does it iterate through and then find the last character when we're typing in dot length?
When you're typing a dot dot length.
Dot length, yeah,
Right,
like
yeah. So that's a
as a
really good
reference.
question. Like if you wanted to keep, like, basically, if you wanted to know the length of a linked list, you probably would have to walk through the whole thing. For an array, it keeps track of it. So I don't know the exactly what's happening under the hood, but basically when an array is created, it's keeping track of its full size. And if that array behind the scenes were recreated, it's still keeping track of all the space it has technically that you don't see, and also what's the total number of elements that are in it. So when you say dot length, it's able to just return that to you. It doesn't have to walk through the list. But yeah, it's a good question because you could see how someone might create a implementation of an array where they're not keeping track of that. And as a result, you might have to walk through it. And so, yeah, you can't, yeah. But by default, dot length, constant time. And lots of things, unless explicitly noted, you can kind of treat everything as constant time, more or less. If the language just gives it to you, there's this understanding that like, okay, you're not like, unless this is a specific case you know about, like, I don't know, that isn't, I actually should roll that back. The reality is actually telling complexity for a real algorithm can be very complicated because it requires that you know the complexity of everything you're calling, which you didn't write most of it probably. And it requires on some level knowing like, well, how does Python make arrays? And so it's understood that you're making sort of shorthand hand wavy assumptions where you're saying like, okay, it's an array. Because it's an array, I can assume indexing and dot length are constant time. I have no idea how Python really did it, but I'm assuming they're a good language. They know what they're doing their best. Let's just assume they did the best version of that. Yeah. Just gonna look at the chat real quick. Okay. Yeah, so these are sort of the order. This is the order in which these like grow, and we'll talk about each one of them in a second. But like if we look at like, so O1 is constant time, we've seen that, and ON, so I'm skipping log n for a second. ON is linear time, it's the average case. It means you're looking at each single element. So compared to indexing, this would be like searching for a specific element in an array. There, unless it's sorted and you know something like that, there's no way to do that. Just, intuitively, there's no way to do that without looking at every element. Because maybe it's not even there. And the only way to find out it's not there is to look at every single element. So something like O log n is interesting in large part because it fits between 1 and n. It's the only thing that fits between 1 and n. And as we learned, this is specifically the case for binary search and nothing else. So when your data is sorted, you're able to do this cut in half each time thing, and that's how you get this guarantee. Similarly, we're going to jump past n log n, which we've not talked about ever yet, and look at n squared. So n squared is, you can call it quadratic time. At a certain point, people stop calling it things, but this is the example of a doubly nested loop. And so an example of an n squared thing would be, let's say you're trying to order a list. Something you could do, which, it's not super efficient, but you could say, okay, I'm going to walk through the list once looking for the smallest element, put that somewhere. Then walk through the list again looking for the second smallest element, put that somewhere. And you keep doing that. And basically, your array is length n. And for each element, you're running n operations in which you're looking for that smallest element. You might say technically like, well, the first time I'm looking for n elements, the second time I'm looking through n minus 1 elements, and on until you're looking at just one element. That is true, but the math of it works out, so it's still n squared. So in that case, for everything, for each element in the array, I'm looking at the whole array once, worst case scenario. And that's like basically a naive sorting algorithm. And we talk about that today. That's one of the assignments is today. If we do an example of bubble sort, so let me just, if I Google bubble sort, and a lot of places have stuff where you can like see it. I love that. Is this an example? I wanted to see like a moving video. There we go. This visual algo. Oh, I've used this one. It's very good. So I don't actually write. So we can see bubble sort in action here. And I believe there's like some way where I can see the actual code being run. So I want to sort this array. And this is actually telling me the algorithm it's doing. But you see what it does is it just walks through it and it swaps the first with the second, the third with the fourth. It's basically walking through it 2 at a time. And if they're, it's looking at 1, 2, 0, 1, and then 1, 2. And if they're out of order, it shifts them, but just in that one direction, and then it does it again. So this might take a minute, which is why I might want to make it move faster. Is that making it move faster? Oh, this isn't making it move faster. So this takes a little while, and this is a great website for seeing this stuff visually, visualalgo.net. I forgot about it, but I used this in college. So yeah, it took a while, but this was bubble sort and eventually did it. And this is an example. Bubble sort is an example of O(n) squared. And we bring that up just because there's this O(n) log n, and just like with log n, it fits between on and on squared. It's, you know, if we can't achieve something as good as on, where we just look at something once, and if you think about it again intuitively, if you're trying to sort an array, you're trying to sort a deck of cards, whatever it is, you couldn't just look at every element exactly once, because you'd have to be a mind reader to know where it goes. That's never going to be enough. At the same time, on squared, looking at every element, and looking at every element for each element feels like overkill. Like if you want to know where something fits, you really have to look at every single other element in order to tell that. And so n log n is like the equivalent of log n, but for this space. It fits in between, and only some algorithms achieve it. And just like O log n kind of tells you binary search, O n log n means a non-naive, a good sorting algorithm. So if instead of bubble sort we were to do, so I think selection sort is another ON one, but let's say we were going to do merge sort, or quick sort is considered the best one on average, and you see there's like a lot of them out there. But if we were to do merge sort counts as O n log n, and you see it works kind of differently, where it's sort of grouping them in this halfway, where it sorted the first two, then it sorted the first four, then it sorted the first eight, and eventually it's sorting all of them. And as it turns out, if you analyze this algorithm, it's O n log n, and you can probably tell that log n part comes from the fact that you have this halving approach. So even if it's, we might want to see that again in slow motion. I'm just doing those two at first, but quickly, and then I do two more, but then every time I do two, now I can do four. And so there's some kind of like having and then putting it all together thing that gives us that log n part. And then the n part is that we have to do it for each element. Okay, so I'll probably come back to this. Okay, so just to finish out this list, I added another section, polynomial time, and cubed and fourth, etc. Whether it's 3 or 4 or 1,000 doesn't really matter. N squared is the common one, but the idea is that instead of a doubly nested loop, this is like a triply nested loop or a 4 nested loop or 1,000 nested loop. It means instead of for every element, you're looking at the whole list. It's like for every element, you're looking at the whole list. And for every element in that list, you're looking at the whole list. These are really bad. Once you're getting n to the cube and n to the fourth, it's very inefficient. But notably, it's very inefficient, but not so inefficient that you couldn't theoretically do it. Like I remember reading that when IBM Watson was a thing, like the Jeopardy playing robot, in order to accomplish what it accomplished in the time, like when it in the time in history when it did, they basically built a supercomputer for it, and they were willing to run algorithms that were just brutally inefficient but did help them. And so there was some algorithm that was essential to how Watson worked, which was O(n to the 7), which is just brutally efficient for an average computer. And part of the rules of the Jeopardy thing was it couldn't be networked, it couldn't be going on the internet. And so it couldn't use like AWS resources. So it really had to be a supercomputer. O(n to the 7) is going to run really poorly, because if I say O to the n and I say, okay, O to the n, that's 10 operations. Well, what about n squared? Okay, that 10 operations is now 100 operations. Well, what about 10 to the 7? That 10 operations is now 10 million operations. And so even for something of length 10, that's brutally inefficient. And it's just worth noting that that's a class where we're saying like that 3 there, 4 there, it's still constant. So it's the n that grows, but that number makes it worse, but worse than squared. But still not the worst. There are even worse cases. Yeah, bubble sort was O(n squared, I see in the chat. So there's even worse cases. So 2 to the n is even worse. Now, as your n grows, like if you thought 10 to the power of 7 was bad, well, 10 to the power of 7 was bad, but what about 2 to the power of 10? Well, actually, that's much smaller, but this is kind of to the point of complexity analysis. As that grows, it gets worse. So 10 to the power of 7, like it's sort of like 10 to the power, how might I show this? So if I say 10 to the power of, or 11 to the power of 7 minus 10 to the power of 7, what's the difference there? Am I doing this right at this point? I'm getting pretty confused. Oh, that's 111. That's why. So basically, if I increment my input size by 1, I'm going from 10 to 11. Now I'm doing so many more operations, right? So that's a big difference. But what about in this case where I say, okay, I'm 2 to the power of 10, but now I'm 2 to the power of 11. I want to do that in the reverse way. Okay, still a much smaller number. I'm not really demonstrating my point, but as it turns, like this is actually an interesting point that we'll see it on the slides. Sometimes for low enough n's, something like 10 to the 7 is going to be much worse than 2 to the 10. But what we're concerned about is the behavior as n gets really, really large. And as it turns out, as n gets really, really large, even n to the 1,000 is not as bad of a case as 2 to the n. 2 to the n gets worse as n gets really large. And then finally, there's n factorial. So factorial is something you most like we implemented the factorial, which is 5 times 4 times 3 times 2 times 1. When you're in this class, basically virtually nothing is in this class on purpose. It's there to demonstrate a point. This is usually the complexity case of something where you're relying on randomness to get you your result. So we're going to see all that now. But any questions? I know it's kind of hard to ask questions at this point because it's so abstract, but any questions about this slide?
I think I'm just anxious to see, not necessarily this slide, but the previous sorting. I'm anxious to see that in code.
Yeah.
You know, I think I'm getting the visual.
Yeah.
I'd like to see how you actually in codes creating a sorting of like an array.
Yeah. Okay, that's good to know. I think based on the size of this lecture and the amount of time we have allotted, we probably will have a fair amount of extra time. And yeah, the best thing you could do in learning complexity analysis is basically compare sorting algorithms. That's why that is such a big topic, because it's kind of been solved at this point, but comparing them really tells you stuff. So we can do that. We can walk through stuff on the visual algo and actually look at how it works. But yeah, moving on to these slides, we just go in detail about each one of these. So constant time like this, indexing is the classic example. It's a flat, and this is really what big O is representing. It's representing a kind of curve. So in this case, it's a flat horizontal curve, which means it doesn't matter what happens to the input size, the performance stays the same. And note that if this horizontal line is all the way down here, well, that means, fewer operations. If it's all the way up here, it means more operations. But we're not really measuring number of operations with big O. We're measuring the relationship between the input size and the number of operations it takes. And so with constant time, it means same number of actions regardless of the input size, which in big O terms is the best, just because it's unaffected. Okay. So now we're going to look at O log n, binary search. We've seen that. So this one grows in relation to the input size, but much slower than the input. So in the case of 1,000,000 elements, or I see 256,000 elements here. Well, if it was constant time, whatever we were trying, let's say we're trying to get the 256,000th element, that would be a single operation, or maybe 10 operations or something, but that number of operations would not change based on the index we were looking for, no matter how big it was. In this case, we're saying, okay, well, my array has 256,000 elements. If I were to look one after the other and it wasn't sorted and I couldn't do binary search, that would be theoretically 256,000 operations I would have to do. But if I put that in here and I say log 256,000, I think that's how it likes me to write it. No, it's not how it likes me to write it. What if I say log 2? Yeah, so that's only that's 18 operations to find any element in this sorted list of 256,000 elements. So it does grow based on the input size, but it grows at a rate that's really comfortable. And constant time is not reasonable for most things that their input size can grow. It's just not going to be the case. So log n is really the best guarantee in terms of this actually changes as the input grows. And it's always connected to binary search, which means it's always connected to the input being pre-sorted. And as a result, you can sort of eliminate a search space by half each iteration. All right, I'm gonna look at the chat quickly. Yep, happy people like Visual Algo. Okay, so that's binary search. Now we're at linear search. This is really what I consider to be the standard case for complexity analysis. As the input grows, so does the performance. It makes sense if you got let's say you were doing something like .map, right? So you have a list of 1,000 elements, and you want to turn that to a list of 1,000 elements where you just took every element and you added one to it. If you need to touch every element, there's no way to do that besides touching every element. So that's going to be O of n. And lots of things that involve arrays are naturally going to be O of n, because how could you do better than that? You have to look at every element. Even if we wanted to sum all the numbers together, that's still O of n, because how do you sum all the numbers together without touching every single number? So, you know, O log n is something to reach for, especially if you're told it's a possibility. But O of n is going to be your standard case for any kind of list, anything that, you know, has an input of size n. By default, you would hope that you could accomplish something in big O of n. Okay, so the next one, n log n. So you see now it actually, you know, unlike here where it slows down over time, now it's starting to grow faster over time, but not much faster. So n log n is the classic example of a good search algorithm. It's actually provable, just like it's provable that for an arbitrarily unsorted set of data that you don't know anything else about it other than it's unsorted, you cannot do better than n log n for sorting. So sorting is not just the worst case, but it's also, in some sense, the best case for sorting. That's not entirely true. If you go on what's that? If you go on a Viz Algo, you'll see this sorting algorithm called radix sort that is ON. But the reason it's ON is because radix sort only works for numbers, and it takes advantage of the fact that numbers have this like you can compare numbers by their like places, I believe. Like radix means like the fact that there's, you know, 10 is an order of magnitude greater than 1. And the fact that it's more digits actually tells you something in terms of sorting. But ignoring that, n log n is going to be your best case for sorting, and so merge sort is an example. Wonder if we could see a nice little visualization of merge sort, not like we saw before, but just a picture. So yeah, this is what merge sort is at its core. And it's why we're getting that n log n approach, because we have to split this up. So we're splitting it up, and we keep splitting it up until we have things of length 1 or 2. And then once we have things of length 2, that's easy to sort them we just swap, we either swap it or we don't. So now we have 6. So now we have these in order by this point. So it's sort of like it grows outward in this double way, and then it collapses in that same way. And then you'll notice here, you might say, well, I have 6 and 5, 12. How do I know how to sort these? Well, I know 6 is the smallest in its spot, and 5 and 12, 5 is the smallest in its spot. So I say, okay, is 5 less than or greater than 6? It's less than, put it first. Is 6 greater than or equal to 12? It's less than, so put that next, and then 12 is left. And that's, as it turns out, I mean, maybe we'll be able to understand this when we go through it at the end of class, but merge sort is going to get us that n log n property, and the log n part is coming from the splitting. Okay, that's n log n. Now here's n squared. An example that would be like bubble sorts. You see, compared to this one, it grows a little faster. This is kind of the standard case for things where for everything you want to look at every other thing. So if you were trying to sort a list, the average person wouldn't come up with merge sort or quick sort. Once you learn those algorithms, they're pretty sophisticated and you will forget them pretty quickly because they're clever. Whereas bubble sort is something the average person could come up with. You say, okay, I'm going to compare the first to the second, and if they're different, I swap them. I'm going to compare the second to the third. If they're different, I swap them. And you keep doing that. But if you do that, you find at the end of it, you're not done. You have to do another loop and another loop and another loop, because you're kind of bubbling the big, you're bubbling the small numbers to the left and the big numbers to the right, but it takes time. It takes multiple iterations for them to get all the way to their right position. And n squared is considered the limit of acceptable inefficiency. So if something takes n squared, it's kind of reasonable. Once something starts taking n cubed or n fourth, you want to start looking at it and saying, is this really the best way to do it? Sometimes it might be, but it could be that you're just doing it inefficiently. The rest of these are basically ways of noting how insane something can grow if not done in a clever way. So in the case of Fibonacci, this is one way we can do Fibonacci, right? And computing Fibonacci 5, according to Python Tutor, is 62 operations. If I double that input size, I didn't just double the number of operations, I basically increased the number of operations by an order of magnitude. And I'm using the examples of 5 and 10 because when I tried to do Fib 20, Python tutors said, I can't do that. I don't do numbers that big because this is breaking my ability to like show you what's going on. So that makes it basically a useless algorithm, because if you could only do it on inputs, up to 10, that's not probably going to be useful in most cases. And the reason for this is, again, because of growth. So if I look at Fibonacci, I wonder if someone can show me shirts. That's funny. He did so much. I have to be more specific. Fibonacci sequence tree. Let's try that. Can I find a good example of it? Yeah, this is an example of it. So the reason why it grows so poorly is that to compute Fib 5, I do 4 and 3. To compute 4, I do 3 and 2, 3, 2, and 1. And at the end of the day, I end up recomputing certain things over and over and over again. So I'm doing Fib 0, 1, 2, 3 times, Fib 1, 1, 2, 3 times. It's no more Fib 1, 2, 3, 4, 5 times. You end up when it comes to Fibonacci, if done this way, and as we'll explore, there's a better way to do it. If done this way, as your number goes up, you're creating a bigger and bigger tree. So it's sort of like the opposite of binary search. And then binary search, we cut it in half each time. And that's what gives us that guarantee. And if like the inverse of log base 2 is 2 to the n, because in this case, instead of being able to cut something in half every time, So, you know, when the n doubles, we only have to do one more operation. This is the inverse, where when the n goes up by 1, we need to do double the number of operations, because we're instead of having things every time, we're doubling the amount of work every time. And then finally, my favorite, this wasn't in the slide deck until I added it yesterday, but I added it on purpose because I feel like it actually makes complexity analysis fun, is n factorial. The classic example of which is BOGO sort, which I quickly wrote right here. This is the worst case you could possibly imagine. I don't think you cannot come up with a class worse than this, because it's an example of how randomness is not an efficient way to accomplish things, at least not if you have a plan. So the way BOGO sort works, it's a way of sorting an algorithm. What it does is it walks through a list to tell if it's already in order, and if not, it randomizes it and checks again. And it keeps doing that. And it's terrible because, I mean, theoretically, this could get it right in not that long because it's a short list. But because of the whole randomness nature, the chance of this getting it right for a big list is insane. It's n factorial, because what are the chances of, you know, if you were to throw a deck of cards in the air and then pick them up, what are the chances they're going to be in the exact right order? Well, according to probability theory, the chance that that first one is in the right order is 1 in 52. The chance the second one is in the right order is 1 in 51. And you just multiply those out and you get a gigantic number that's n factorial. So BOGO sort is terrible, but it's also very fun to write. Yeah. Okay. So that's all of our cases. And now this is the chart that you'll often see that this tells you everything next to each other. This whole like horrible, bad, fair, good, excellent, not really true, as in ON squared is not horrible. It's fair in my mind. It's only once you start getting here that it's horrible. Totally reasonable. I mean, all of these are reasonable. It's just that, you know, O1 is the best. It's not growing at all. O log n, it's barely growing. ON is growing how you think something would grow. ON log n is pretty good compared to its, you know, big sister n squared, which is sort of the definition of like, maybe you could do this better. And then beyond that, it just gets real bad real fast. As you see, ON factorial, it's literally just like, you know, a straight line up almost. You know, by the time you're at, you know, a handful of elements, it's impractically inefficient. And that's cool to note. But, you know, in practice, it's just like you want to be able to notice it and know about it. And most of your LeetCode problems are not ON factorial, Kelvin. I'm sure of it. It's actually one of those things where it's just like, to write something ON factorial, you actually have to be very intelligent, because it's like getting a 0 on the SAT. You have to really know what you're doing to do that poorly. Because it, like, your average, like, that's just not what happens unless you're trying for the worst thing you can imagine. Yeah, it kind of does look like a sunrise. And I feel like it's worth saying in terms of this whole n cubed, n to the fourth thing. There's a guy I knew in college who I mean, maybe he got better over time, but in our first computer science class, he would do things where he was like, is it bad that that was like, you know, a four nested loop? He's like, that's how I did it. And so he had a tendency of just putting things, you know, nesting loops like crazy, and that's bizarrely inefficient. But at the other end, he's probably the most successful person I know right now because he runs a company. And like the company is like making money. They're like a video game company. It has to do with Bitcoin. I don't know if it's actually going to work, but there is kind of this point where you can be brutally inefficient and you'll learn. Like, I doubt his video game has these terrible algorithms in there, but there's really first and foremost, you want to solve a problem. And after you solve a problem, if it matters, you can worry about efficiency. It probably doesn't matter for most things, because there's often this in practice, in terms of performance, there's often this idea of like a bottleneck, which is like, you might have optimized the hell out of this tiny little part of your program, But it turns out that your program is slow because it depends on the internet, and networks have a certain amount of latency. There's nothing you can do about that. And basically, even though you made some part of it brutally efficient, it doesn't matter because there's this weighting that happens anyways that you can't control. So you don't want to prematurely optimize. The company's name is, I think, Bitcraft. Let's see. I find the crypto stuff very iffy. But this is it. I can tell you, I signed up for this free alpha thing like 5 years ago, and I haven't gotten my invite. So, but still, it's like, it's a whole thing. It's pretty cool. Pretty cool. See if we can find Tyler.
What is that?
What?
What is this?
This is my friend's video game. He was making n to the fourth algorithms in CS 101. Not that that is the worst thing in the world. Okay, we can't see people's actual. Oh, there we go. I don't know who any of these people are. Investors. Okay, they get faces. The actual employees don't get faces, including Tyler himself. Okay, whatever. Just a video game.
I have this is something I've been thinking about, this graph in the slides, and it's the same thing if you look up big O notation on Google Images and you see all the graphs there, like the other one, like the colored graph that you were showing earlier. Or yeah, that one. Like it has the y-axis as operations and the x-axis as elements. But if that's true, shouldn't the line for O of n be at a 45-degree angle up through the middle, and all the others be different as well? Like
Yeah.
and it's like every graph that you look at on Google as well. It's all like just like this.
Yeah. So basically,
Oh,
this is not really about big O. This is about the problem of trying to compare things in a graph, because basically, if you're trying to include O(n) factorial, if you're trying to distinguish between these, basically, if you had O(n) going right through the middle like that, all these other ones would just be, you know, super to the left. So
Okay.
that's the only reason. Like, it's just a way of trying to fit all the information together. It's not so helpful to see all the information together. Yeah.
That makes sense. I just couldn't help but think it. It was just on my mind. But
Yeah, and I feel like honestly, graphs like this would be better if we just remove this whole section, because these are the ones you really want to compare, because they're the ones that, practically speaking, you'll actually see. And based on this, you're not really getting to see how like O1 is not quite O log n. Like, they're all getting squished together in a certain way. Okay, I see Kevin shared something on Reddit. Hope this is safe. Would this technically be O(n)? Interesting. This is nuts. What is this? What is this exactly? It's playing chess? Yeah, well,
Yeah, so I guess technically he's doing if else for every single possible chess input.
okay, yeah. So, well, the thing is, I think actually in this case, things are probably constant time, in that this is an interesting thing that can come up in interviews. The chessboard has a fixed size, right? Like, what is it? It's 8 by 8, or what is the size of a chessboard? You're the chess guy. You're the guy who's bringing chess into this.
I don't know.
It's 8 by 8.
Okay, so it's 8 by 8. That means there's 64 spots. The input size cannot grow. There are only 64 spaces in a chessboard, which means they can actually check every single space. I mean, technically, this would, if they're looking at the player's input, and the player's input, I don't really know chess well enough, but if this refers to a specific, you know, horizontal row and vertical line position on this chessboard, there's only 64 of those. So there's nothing, you might think this is bad style, but there's nothing complexity-wise inefficient about this. And also, even if you consider it bad style, the interesting thing is, in video games, you often see these sort of more primitive approaches where you just have long lists of if-else statements, because that's kind of like the best way to think about it. or it doesn't overcomplicate things.
Isn't this the worst way possible to program it though? Because you're actually gonna have to program out each individual move when there's like millions of combinations of positions that everything can be on in the board.
Yeah, that part is true, that if you're taking a unique version of the board, and then for each unique version of the board, you're checking that player's position, you're right. That's going to grow to an insane degree because of how many combinations there are of pieces on the board. That's probably like I don't know if it's technically it, but it's like 64 factorial for all the combinations of the board, and then add to that 64 different options for what the player could do each time. The numbers are probably a little smaller because you can't do everything every time, but yeah, like in terms of actually writing it, this would be an insane way. Ideally, you would want to learn some patterns through this, but this is actually to the point of like part of what machine learning is, and that's a pretty advanced topic, but what machine learning is basically saying, this is too complex to write an algorithm hard-coded. Can I write an algorithm that's a pattern finding algorithm? And that pattern finding algorithm will find the patterns, so that algorithm itself is what's going to produce all of these. Because it would be brutally inefficient for the programmer to write it themselves, not necessarily to run it. Very interesting. There's illegal moves according to, yeah, interesting. Right, not including illegal moves. Della is asking if it's a common interview question to sort data in a certain way. I feel like not anymore. I really wonder what the modern interview is like, especially for the average like code platoon graduate, just because these questions have been asked enough that places like Google, they're in this, they're just creating new problems all the time. And so knowing about sorting, knowing the complexity of sorting, knowing that you can sort, that is going to be a useful tool, but they're never going to ask you to straight up, do merge sort. Instead, they'll ask you a question that if you're clever, you see it and you go, oh, they're asking me to do merge sort. It's just the question kind of disguises it. So it's not, you'll almost certainly never be asked to directly do one of these. And my attitude is like, unless I'm studying it, I don't remember how to do quick sort. I could probably figure out merge sort again, but it would take a while. It's not so common for people to remember outright how to do this stuff. It's mostly important just that you can talk about it and that you can say, oh, well, if I want to first sort the data, that's n log n. So I have to take that into account. Here is this gigantic list. You're not expected to remember or know this, but you'll see these on the internet. And this is kind of how data structures and algorithms and Big O all come together, where someone can say like, oh, well, I need this data structure and I have to have constant time access. So I see, yeah, so I have to have constant time access. Okay, arrays are the only option. Not really true. Technically, a hash table is near constant time. It gets complicated to think about some of this stuff. There's certain concepts we're not even introducing, but like hash tables, are like a dictionary where you look something up by a key. That's nearly constant time because of this concept called amortized, which you don't really need to know about. But basically, you can use a chart like this to say like, if what I plan to do is just like insert and delete constantly, well, maybe I want one of these, but I have to recognize access and search are not as quick. And so you can kind of use these sorts of things. Oh, I see, this is average over here. You can use these charts to figure out what you need for a given situation. Really, I mean, to be honest, people don't look at charts like this that often in a practical way, but it's just a way of seeing all of it come together.
If you do like the LeetCode code 75, are you gonna end up learning all of these data structures?
Yeah, probably. So I think I know what you're talking about because I did that. I did some of that last semester for like coding interview review stuff at the end of the course. What is that called again? What is that, you know, curated list of leak code problems called?
Yeah, it's just called LeetCode code 75.
It's the blind 75.
Yeah, blind 75. That's the one I heard of, right? So let's try blind 75. Where's the actual website? Is it this?
Yeah, it's neat code.
Okay. So, yes, exactly. As in, we're going to look at these 75 problems, and just people said, like, you know, just narrowed it down to some to care about. And it's like, okay, you have 8 problems in arrays and hashing. I'm not sure why they treat those as one section. We'll talk a little bit about hashing laters. Problems that can be solved with 2 pointers, problems where sliding window is a thing, stacks, binary search, linked list, trees, tries. Tries are a unique thing. Maybe we'll talk about it eventually. It's not super important, but there's just a lot theoretically out there. I don't remember how to do a heap, which is sometimes called a priority queue. It's a data structure that is useful for getting, like, if you only care about like the most recent or the largest. Let's say you had a list of, let's say you had lots and lots of numbers and you wanted to keep throwing the numbers in a bucket, but you wanted to always remember what the largest number was. And you want that if you then remove that largest number, it automatically knew what the second largest number was, but it's not necessarily all in order. You can't get the 5th largest. You only can get the largest one at a time. That's a heap. Backtracking, it's just backtracking comes up with graphs. It's the idea of like, essentially like you lost your wallet, right? Well, you use a backtracking algorithm. You say, where was I last? Well, where was I before that? Well, where was I before that? And you keep doing that until maybe you find your wallet. Graphs, if you're trying to get from point A to point B, that's a kind of graph. You follow different roads. Some are one way, some are, they can connect, they can loop. Advanced graphs, dynamic programming is this whole thing. I've prepared a lot for dynamic programming interviews, never got one question in it. It's a notoriously difficult, weird part of data structures. It actually is a funny story though for military people specifically, I find, because the guy who invented dynamic programming, you might ask, well, why is it called dynamic programming? That name is kind of a misnomer. It's basically this guy who's a mathematician who worked for the military in some fashion. He had a boss who he knew hated math, and he wanted to do this research, but he knew he couldn't get go ahead if he said, like, I'm going to do math. And so by calling it dynamic programming, it was like a marketing thing. He convinced him that like this would be useful for scheduling purposes, apparently. And it's just like, literally, it's called this because it let some guy convince some other guy who didn't understand to let him do some work. The dynamic part is meaningless. But they're sort of notoriously difficult, weird problems. We might get into them at the end of the semester. Greedy problems, that's just an approach in which you try and do the best thing each iteration. I don't even know what intervals means, math and geometry, bit manipulation. You could still get problems that fall outside of this. The top level places like Google, they'll ask you questions that are designed to sort of even, test a person who studies this stuff like crazy because it's a problem you've never seen before. But for the most part, much less than this will be fine in an interview. I've never seen bit manipulation in an interview, or math and geometry, or dynamic programming, or even I've seen like one graph problem, but at like a top level place. I've never seen heaps. Yeah, it's really just this stuff up here. So hopefully that's helpful. I see it is 9 or 10:25 now. We've been going for at least an hour. Gonna let you go in a second. The last thing here is just This ends up being on the last slide here. What we do when we come back is just like some examples where we work through coming up with what Big O is for arbitrary algorithms. But there's some rules to Big O that without getting into the math, we really can't explain them, but well, I guess we can a little. So whenever we're working with Big O, we think of n as a number so large it might as well be infinity. And you've probably heard like what's double infinity? Well, it's just infinity, right? You're not actually changing this limit by doubling it. So if we, the difference between n and n plus 1, that's still n. And by the same token, n plus n, 2n, 3n, 1000n, whatever it is, as long as it's a constant, that's the same as O of n. So that's like, if I had O of n means like I'm looking at every element once. Well, what if for every element I look at once, I do 1,000 operations? Not related to the input size, but always 1,000 operations. Even though compared to something where you do one operation n times, that one operation is going to be it's going to be 1,000 times faster. But they still count as O of n because it's just about the input size. And yeah, so a nested for loop would be, or a for loop is O n, a nested for loop is n squared, and that concept continues. And just in general, you drop constants. And if you end up in a situation of like O n squared plus n, that's just O n squared. So you drop constants and you always take the biggest one to represent the worst case. And that's all you care about. And as we see when we walk through specific examples, when you're actually trying to practically find the Big O for a problem, you're kind of saying like, okay, I did this, maybe that's O of n, and then separately I did something else. So not nested, but separately I did something else. Oh, that's O n squared. Then it's n plus n squared. Well, that's just n squared. But we'll get into that when we come back. Let's take a 10-minute break and come back 10:35 CST. I see there's a lot of chat, so I'm gonna look at it now.
Hey Ben, have you ever played Sudoku?
Yeah.
Have you ever gotten like kind of into Sudoku and like played it for a while and actually like learned some of the more advanced like methods or algorithms to solving puzzles? Because that's exactly what this reminds me of. Like when we were looking at that blind 75 and it was listing out all of those like different algorithms you would use or different data structures you would use to solve those problems. Like I used to be pretty big into Sudoku and it's like the same thing. Like as you go up in difficulty, you just have to learn all of these like increasingly complex methods for solving the boards. And like, I don't know, it just reminds me of it so much because that's like exactly how it is playing Sudoku. But I really enjoyed it. But then I got to the point where I was like, why am I putting myself through like learning all of these annoying and like dumb complex methods to solving Sudoku when I'm just doing Sudoku? So I ended up just stopping at some point because I was like, this isn't worth the trouble. But that is like very similar to a degree, like to actually solving like leak code problems, it seems.
Yeah, I definitely never got that far. Like I kind of quit on Sudoku at a certain point, even though I also got into it at a certain point too. But you're exactly right, as in like your n, as you see here, they're gonna like, I think at some point they use n and m because sometimes you want to keep track of two variables. But basically your n could describe like, the dimension of the Sudoku board, which could be arbitrarily large. It doesn't have to be 9 by 9, right?
Right.
And then once you have that dimension, like data structures, like this 2D array called a Sudoku board is a data structure, and data structures necessarily demand algorithms. So, there's certain rules. How do you, solve the next number or whatever it is you're trying to do in this Sudoku board? And the nature of the algorithms are that they're going to be different. Some of them are going to be more performant than others. Some of them are going to accomplish things others can't. And so now you get the concept of like complexity analysis. But even if computers were never invented, the math of stuff like data structures, algorithms, and complexity analysis is enough to talk about essentially math puzzles, which is why it predates computers, which is cool. So
Yeah,
yeah, I mean, if you tried to write a Sudoku solver in code, you would find all this, like you would have to account for exactly how all of it works.
yeah. I just before I ended up like kind of getting into Sudoku, I never realized how insane it gets like at the top levels. Like obviously I never made it very far compared to like people that are actually really good at it. But like the people that are like world championship Sudoku players, it is insane like how smart they are and like how much stuff that they ended up learning and practicing to actually get there. Like I never realized that Sudoku was that deep. But it really is. It's very cool.
Yeah. Yeah, and I imagine it's like one of the cool things about doing things like Sudoku is that you can literally see how your mind works, and you're like, oh, there's a computer in my mind. Like, there's also this part of you that's like the ego that like likes food, or I don't know. Like, there's a part of your mind that's not necessarily about crunching numbers, but there's this part of your mind that is very good at crunching numbers, and you can see it work, and it's like I think that intuition about how your own mind solves problems is very useful in coding in general, because you just think like, how would I solve this? And then you figure out how you might do that in code. But like your brain also thinks in this step-by-step approach of like, okay, I'm gonna like it's usually can think a little larger or more parallel than a computer can, but still like it all boils down to just like you look at something, you get some definite information, you look somewhere else, you get some definite information, you compare the two things, that lets you know some next move to do. It's cool.
Is there like a competition for like solving coding challenges or leak code problems? Like there has to be, right?
I'm sure there is. I mean, I know that in college they used to like Google has this version of like Quiz Bowl where it's like a recruiting thing for them, but they invite computer science students to come to their offices for like a day, and there's this like in-person competition which is like leak code, in which you're given like 5 problems, you can split it up how you want, and people solve them and then hand them in. And I just remember when I went to this thing, there were maybe like 10 schools involved. One school got like all 5, another school got like 4 of them, every other school including mine 0. So
Wow.
it's like, well, just because I had not like they're hard problems.
Yeah.
And it's like you said, you have to be like very good and practice at it if you're going to be good at like seeing a new algorithms problem and in a short period of time solving it. But I feel like I'm not sure that there's a competition for something that would be like fully remote, but there's definitely stuff out there. And
Hey
honestly,
Ben,
yeah, yep.
it seems like when we're choosing how to sort um a specific challenge or problem, uh we have to know whether it's ordered or unordered or maybe the input size, right? That's what seems like is what's going to make our choice on what we choose, right? So in most like situations where we want to like try to order it so we can make it a little bit easier and make it a little bit faster if we're allowed to, right?
Yes and no. So basically what you're saying is like, okay, well, if the input is already sorted, I'm able to do binary search, right? And binary search is a real good one. But if the input is not already sorted and you want to sort it first, how do you do that? Well, you have to use some kind of sorting algorithm. And the best case scenario for a good sorting algorithm is O(n) log n. And that means that you have to do an O(n) log n operation before you could even start doing binary search, which means if you're not getting the input in a sorted order and you're going to sort it yourself, you're already kind of making you're already getting a worst case complexity, because sorting itself is a pretty expensive operation.
Yeah, that makes sense. I was just trying to think of like a decision maker for when you come across like a specific challenge. Like, okay, if I recognize this pattern, or if I recognize like the input's pretty big, maybe I'll choose this to go with.
Yeah. I mean, what you're saying is definitely true in that it's hard to put in words like, okay, these are the strategies you want. But if you do enough lead code things, your brain gets this sort of second sense of saying like, oh, this reminds me of that. I'm going to try this approach. Or you see something and you're like, I know this is going to want a recursive approach. If I try something non-recursive, I'm gonna run into issues. Let me just, go down the recursive route first. And that kind of intuition only comes with doing it. Yeah. Because like a lot of these problems, especially the first time you see them, they're hard and it's not intuitive. And it's only once you see a bunch that they can start being intuitive. But if a problem is new to you, like basically if you never saw a linked list type problem, like reverse a linked list, and well, not with reverse linked list, but there's certain problems where like if someone asked you to, they gave you like a graph and they said find the shortest path. And if you did that without having seen these shortest path algorithms before, if you did it well, you kind of deserve a Nobel, not a Nobel Prize, but that's what getting a PhD is, as in you never saw that. Like the reason why someone like, if someone says Dijkstra's algorithm, it means this one shortest path algorithm. And like this is one of the big names after like Turing. This guy Dijkstra is one of the big people. And if you can solve what he solved that made his name in real time on an interview, that's nuts. That's why it's probably not going to happen. It's too clever to come up with in real time. I wonder if he's alive anymore. He's probably not. Oh yeah, I love his quotes. He's got good quotes.
Yeah, I remember you brought him up because you were talking about it's like one of the things you have to know for your the Google questions, right? Is that correct?
Yeah, I mean, definitely with Google, graph algorithms tend to be big, and Dijkstra is a very important name when it comes to graph stuff because he solved the basic problem of how do you efficiently find the shortest path from A to B in a graph, from anywhere to anywhere else in the graph. That's kind of a central problem. So if you think about that problem in the real world, it's if you have a map and that map is full of roads and you pick one point on the map and another point on the map and you say, how do I get from my start to my destination? What's the best path? The best path, the best algorithm to find the best path is Dijkstra's algorithm. And that's like a central idea, right? I mean, Google Maps could not exist without that. And there's been like additions to that over time. There's something called A star, which is Dijkstra's algorithm, but it includes the heuristic meaning like the shortcut basically of direction. So it's like, instead of looking at any nodes behind me, I'm going to look forward first, because chances are the shortest path is going to be more or less in the direction I'm going. And maybe I got to go around sometimes, but I shouldn't look equally forward and backwards. And Dijkstra's algorithm is not for space necessarily. It's for just graphs. Maybe the thing behind you is could be the shortest path. I don't know. Kind of hard to explain without getting into it, but looks like we're at time and we are back. I see people are writing this in the chat. Honestly, that whole dopamine hit thing, it's not a joke, as in like, I feel like that's a little personal to say, but I didn't go to college when I was 17 or 18. I was like super depressed for a while, and I worked at Staples, I worked at GameStop. Not that those are bad places to work, but I didn't have like a great career thing going on. And then I got into coding and I had this dopamine hit, and that just like motivated me. And I just could not get enough. I just kept doing it until I eventually went back to college for it and did pretty well in it. But don't underestimate the power of that dopamine hit of actually solving the problem, because it will distract you from it's not the best approach. It doesn't solve things outright, but there's something very good about being able to focus on something, and then when you get it, you're like, oh man, I did it. I mastered this one tiny bit of reality. So that is cool. Okay, so I guess I'll leave some of this open, and I'm going back here now. I'm just going to check the calendar real quick. We have another hour and 20 minutes, I believe. Because I think we are going to have some extra time, and that's good. We'll be able to do some stuff. So most of these slides are what you have seen, but yeah, I mean, we just have some examples: constant time, linear time, just examples of algorithms that actually would fit that. So I guess we can review these a little. So like, does anyone want to tell me why this first example, append to list, is constant time? Honestly, this is a terrible example, I'm realizing, because we have no idea how mylist.append itself works.
It's just one operation.
Yeah, exactly. I mean, to me, this is a little silly because it's like we're just passing off the problem to Python and saying, I hope Python did it right. But indexing from an array would be the classic constant time. Just you can look that up immediately. Binary search is logarithmic time. For linear time, why is this one linear time? So find item greater exists.
You're looking at each element.
Yeah, so we're looking at each element, and notably, because it's find item greater exists, the minute it finds an item in that list that's greater than the input, it's going to return true. So if I'm looking at either of these lists and I'm looking for 1, that would be a single operation. But we don't really care about that. We care about the worst case scenario. The worst case scenario is we're looking for an element in the list that is bigger than any other element in the list, which means we have to walk through the whole list. And then I guess at the end, we return false. And in that case, it's ON, because we have to potentially look at every element in the list. Okay. N log n, we're saying there aren't many simple algorithms like that. But we actually will get into this if we have time at the end, because that's the guarantee for a good sorting algorithm versus a bad sorting algorithm. So here would be an example of a bad sorting algorithm. It's not a sorting algorithm, but it's the same concept more or less. Find double exists. We're going to look through each element in the list, and then we're going to look through each element of the list again. And if that first element, double it, is equal to the second element, then we return true, otherwise false. So I guess in this case, we look at 4. And while we're looking at 4, we look at, well, the way this is written, we actually look at 4 twice, but really we look at 4 and we compare it to, 4 times 2 is 8. So we compare 8 to 9, 8 to 5, 8 to 12, 8 to 2. We don't see 8, so we don't return true. Now we move on to 9. We compare, if this was written a little better, it's not, but we compare 9 times 2 would be 18, 18 to 5, 18 to 12, 18 to 2, it's not there. Then we compare 10 to 12, 10 to 2, it's not there. Yeah, so I think this first one returns false because we have to look at 5 elements, and for each of those 5 elements, we look at 5 other elements, and that returns false. Something I think is worth, I just want to write this out because I feel like it is worth seeing. So whenever we're talking about this stuff, I'm saying, like, let's say I'm going to say this, I'm gonna write that, identical find double algorithm, even though it seems a little contrived. So this algorithm right here, I have the small list, I have the large list. I guess I'll save this exactly where I am, and I'll call it, okay, we're in day 3. I guess I'm just going to save it right where it is at day 3 at the surface, and we'll call it find double.py. And this way I can run it. So I can say Python 3 day 3. So if I run that, nothing happens, and that's because I'm not printing anything. So we're just gonna print it. Okay. So they're both coming up true. I actually don't understand why. If I were to look at this, it looks like, so how this is currently written, let me get rid of the small list. I guess we'll just do the large list. It looks like what I'm doing is I'm saying, like, I'm taking this whole list, right? And the first thing I'm doing is I'm saying for X in list. So I'm first looking at 6, but then I say, you know, so X equals 6, but then I'm saying for Y in list, which means Y is actually looking at 6 versus 2. And then I'm checking if X times 2, so X times 2 is going to be 12 in this case, is identical to 6. That's obviously never going to be true when they're the same. When does this actually become true? As in, is one of these numbers the double of another number? Why does this return true?
Hey, Ben, it's returned true no matter what.
Yeah, I don't know. I apologize for this. This sometimes happens where if a lecture has not been looked at in a while, it's not quite up to snuff. No, but this one's still returning true seemingly.
Well, 3 is, or 6 at index 0 is twice 3.
Yeah, there we go. Yeah, exactly. So by the time we hit 3, oh, and that's actually a reason we want to do this, that if I looked at 6 compared to the rest, I would say like, okay, well, is double 6 equal to 3? Yes, or like no, but by the time I get to 3, I still want to compare 3 to 6. So yeah, I mean, I might this is one way to do it, but something you might think is like, well, why am I looking at 6 compared to 3 and then later 3 compared to 6? Like, why not look at, for 6, look at these, and then for 10, look at these, and then for 9, look at these. And that is actually a better approach. Like if I were to rewrite this myself, I would write something like, okay, for X in my list, I know there's a good way to do this in Python with slices. Honestly, it's probably simplest to do it with ranges. So I'm going to say like for X in the range of the length of my list. So that's going to start at 0 and go to 0, 1, 2, 3, 4, 5, 6, 7, 8, 0 to 8. And then I'll say for, I like to call these I and J. So for I in range, you know, length range up to length of my list. For J in range length of my list, then that would still be like I and J. So if I do it this way, it works, but I'm going to be comparing 6 to 6 first. And what I want to do is compare, yep.
Could you subtract I from the length of my list for that J row on line 6? Does that actually solve the issue?
Well, I still want to compare to the end. It's that I want to compare 6 all the way to 13. But what I don't want to do is compare 6 to 6. And by the time I'm at 10, I don't want to compare 10 to 6 or 10.
Could this not be a variation on the sum pairs problem, where you kind of have a list of all the doubles and then you look for those in the original list? And I guess that's what you're doing, but
yeah, I mean, this problem is kind of arbitrary. I'm not sure which problem you're talking about, but there are a lot of problems like this where you look through a list and then you want to look through not every element for every element. You really want to look through every other element for every element, and you don't want to repeat things, because once you compared 6 to 10, by the time you compare 6 to 10, you compare 6 to everything else. By the time your I is now 10, you don't want to compare 10 to 10, but you also don't want to compare 10 to 6. You already did that.
You can put a starting value for range as the index of I.
Exactly. Or rather I plus 1, I think, because as in this is going to be 0. So I want to compare 0 to not 0 initially, but 1. And I guess a way to do that is I could print it out. So I'm going to print I and J just to see that they make sense to me. I don't really care about the answer right now. And do they make sense? Is this everything? No. Okay, so it's 0, 1, 0, 2. So I'm comparing all of them. And let's say I want to say, like, I'm not really concerned about there being an answer. I just want to see it iterate through everything. Yeah, so I'm going to compare 0 to everything else, and then 1 to everything else. And you see how, like, 0 is compared to 1, but by the time I'm getting to 1, I'm comparing 1 to 2, not comparing 1 to 0 or 1 to 1. And by the time I get to, 3, I'm comparing it to 4 first. And by the time I get to 6, I'm comparing to 7 first. And by the time I get to 7, I compare it to 8 first. And by the time I get to 8, there's nothing else to compare it to. Yeah, so I like this approach. But even if we do this, like, we're going to put this back in. So there could be a worst case scenario here. And also for this particular problem, I really want to check it both ways. So I want to say, like, if I times 2 equals j, or j times 2 equals I, because those aren't quite the same thing. Because if I was looking at 6, I being 6 and j being 3, I wouldn't want to miss that. And so 6 times 2 is not 3, but 3 times 2 is 6. But let's just say we're in a worst case scenario where it's not true for any of them. This is still big O of n squared. Why? I feel like this is important to see. So have you ever seen this equation that tells you if I want to sum up until 10 algorithm, I don't know how to write this exactly for the search, but if I want to find the sum of all numbers in a row, some sequential algorithm, let's try that. I don't think that's it. Is that it? Well, I'm not sure I'm going to find it, but this is actually a mathematical idea that, has nothing really to do with computers. It's just, if I have a list like 1, 2, 3, 4, 5, one way of finding out that solution is add 1 to 2 to 3 to 4 to 5, which would be 9, 10, 11, 12, 13, 14, which would be 15. But it turns out there's a relationship here in which I could say it's something like n minus 1. I don't remember it. There's a way. Without remembering what it's called, sum first 10 numbers equation. Like a school kid figured this out at some point. It's a very simple algorithm. And how does it work? You shouldn't have to look at each element.
Was that Milton Babbage that figured this out?
Yeah, probably. When he was a kid, I guess. Yeah. And that's the same as like Milton Babbage, Charles Babbage. There could have been multiple. Yes.
Yeah, that's Charles Babbage. I'm sorry.
Okay. So Charles Babbage sum algorithm. I cannot remember the exact equation. I don't think I'm going to find it right now. It's a shame because it's something like n minus 1. Let's say I was trying to add all the numbers between, I think that's it. As in, if I'm trying to add all the numbers between,
I guess you're just getting like first one plus last one divided 2 multiplied to the length of the array.
Is that it? So I say 1 because that's always going to be the first one in this case.
And the last one, 5.
5 is 6.
Divided to half and divided to 2.
2 is 3.
Multiplied to a number of elements. So there's 5 elements.
The total number of elements, which is 5, which is 15. And let's see if the same thing works for a list of size 10. So I just know off the top of my head that if you do this, it should be 55. And so that would be 1 plus 10 is equal to 11. Divided by 2 is going to be 5.5 times 10 equals 55, right? So the equation there is essentially, if I'm trying to find how many operations, or how do I think about this? If I have a situation where I'm adding 5, 4, 3, 2, 1, that's going to look like 1 plus n. That whole thing divided by 2, and then that whole thing multiplied by n. And so the question is, if I'm looking through each element in the list, and then for each other element, I'm looking at each element, or sorry, if I'm looking at, you know, all of these numbers, and I'm comparing 6 not just to 10, but I'm saying 6 compared to 6 compared to 10, you know, and then 10 compared to 6 compared to 10 compared to 9. So if I'm really looking at every element for every other element, that would be 10 times 10, 100. That's n squared. The question is, if I'm looking at 6 compared to 10, 6 compared to 9, etc., and then by the time I'm at 10, I'm not comparing it to 6. I'm not comparing it to 10, only comparing it to 9. So it's like the first time I compare it, you know, n times. The second time I compare it n minus 1 times. The third time I compare it n minus 2 times until I'm eventually comparing it just 1 time. So the question is, what is the complexity of n plus n minus 1 plus n minus 2 plus ... plus 1? And the answer is this equation over here. And that's why complexity analysis ends up being math, because that thing on the left is the same as this thing on the right. If we multiply this out, we get something like, I mean, I don't know the full thing, but you can see the ends are what matter. So, oh, I guess I can do it. We're going to get n times 1 is n plus n to the power of 2. And that whole thing is going to be divided by 2, which we could say is the same as 0.5 times that. And based on the rules of complexity analysis, I first drop that, I drop the factor, whether it's, you know, bigger or smaller than 1. And then once I'm here, I say, well, n squared is bigger than n, so I drop anything that I plus, and so the whole thing ends up being n squared. That was kind of a digression, perhaps, but I think it's good to see it, because when you see it, you actually see how, like, right, in the case of n plus n minus 1 plus n minus 2 plus n minus 3, at least according to complexity analysis, it's no better than it would be if we actually looked at every element. In terms of actual efficiency, yes, it is better. But in terms of complexity analysis, no, it's not. Okay, so coming back here, that was the example of the quadratic. Exponential is this Fibonacci thing, where we're doing Fibonacci poorly. This global thing, you might not have seen it before, but in Python, that's how you create a global variable. So that's a way of referring to that calls thing from within here. I'm not even sure if that's necessary, but I guess this is, otherwise it would be creating a new variable, I guess, I'm not sure. But this is bad because of that chart we saw earlier, where it's going to do it over and over and over again for each time. So that's another one that we might just want to see. So I'll change the name of, like, I'm just using this as a scratch pad, but I'm going to change the name of this to fib. And I'll say def fib, and we're going to do it initially the naive way, but we're also going to keep track of this idea of number of calls. So I think I could just do that like this. We'll see if that works well enough. But I'm going to say fibs n, and then I'll say if fib, oh, sorry, if n is identical to 0, or n is identical to 1, I want to return 1. Otherwise, I will return fib n minus 1 plus fib n minus 2. And then we'll actually call it here, where I'll say fib 10, let's say, and we'll keep track of the total calls, because every time fib itself is called, I'll say calls plus equals 1. And then maybe I'll print it each time, where right before it's finished, maybe I'll say here, like, I'll say print computed fib, and we'll put the n in there, equal to 1. And over here, maybe I'll do it like this, where I'll actually first calculate it. I'll call that like result is equal to that. And here I'll say computed fibs n is equal to result, and then I'll return the result. And I guess I don't really need to print the result of fib 10, but I will. So let's actually run this now. So same thing as here, but now I called it fib. So doesn't, right, okay, so this is apparently that globals thing. I have to say that calls is a global variable, that it's outside of the function. Otherwise, it assumes it's inside of the function. That'll hopefully be enough. Let's try that again. Okay, so let's see what we see here. Might even help to move this whole, can I move it? No, I'll just make it bigger. So it can be hard to picture it. Python tutor can help, but basically, in order to compute fib 10, I had to compute fib 8 and 9, and eventually that resulted in computing fib 1 and fib 0. So it's like fib 1 and fib 0 were computed in order to get fib 2, and fib 1 and fib 2 were computed to compute fib 3. And you end up doing operations over and over and over again. And I guess at the end, I actually want to say something like, let's do this. I'll say computed fib 10 in this many calls. Oh, and I actually should call it. Okay. So let's do that again. So computed fib 10 equal to 89 in 177 calls. Now let's try, I guess to make this as computer sciencey as possible, I'm gonna actually have this thing called input now. It's the input I pass here, and it will be the input I pass here. So let's run that again. Wow. So now to compute, even though we just doubled the size, it took 21,000 calls versus whatever. I can't even see the original one anymore because of so many calls. I mean, I might take these out at a point because, I don't want to see it. But still, one takes a lot longer to run than the other. And if I were to do this twice and compare them, it would look like this. Okay, 100, so like basically we doubled the input size, but what's the relationship from here to here? It turns out it's 2 to the n, but that's a huge change. And if I try to do it one more time, like I don't even know if this one will finish. I think it's going to run for oh no, okay, it's okay. But still, it's getting bigger and bigger, and all we're doing is doubling, not even doubling the input size in this case, just adding 10. So, I could theoretically do 40 there, and see what doubling the input size is. Now it's really taking time. It's still going to compete, but behind the scenes, we're doing so many extra operations than we need to do because of how we wrote it. See if this does ever finish. Ah, good point. We're also not resetting calls. That's an amazing point. I should be resetting calls between each thing. But as you can see, it doesn't even want to do that last one. And still, even if we're resetting calls, it's a pretty big difference still. That first one wasn't making too big of an impact. Okay. But it can't even go up to 40. It's really not able to run. So we look back here, we're talking about how this is exponential time, and then we mentioned making improvements. So in terms of ON squared, I'm not sure what improvement was actually, oh, right. So this is going to check both ways. That's a kind of improvement, but there's a pretty important improvement here in terms of memoization. And the way this is written is not, I find single letter variables kind of hard to follow, but if we look back here, we could say like, okay, I have, these two cases here, at least those run, and I'm keeping track of this calls thing. Maybe I should like reset it each time. Okay. So this was fib, but I'm going to rename this to fib naive. And I'm calling it naive because it's a way of doing things that works, but we're really wasting a lot of time because we've computed we're computing 0, 1 over and over and over again. And that's because we're starting at that 10. We're trying to do 9 and 8, which is trying to compute, for the 9, it's trying to compute 8 and 7. For the 8, it's trying to compute 7 and 6. And we're just going to repeat those so many times that we end up recomputing things over and over and over again. And the alternative is we start from the bottom. And every time we solve something, we remember it. And that's called memoization, which is a fancy word for just saying we remember what we did previously, so we're not redoing any work unnecessarily. So I'll call this one fib smart. And the way this is going to work is if we want to get the nth Fibonacci number, we know we're going to have to get those other Fibonacci numbers before it. So I'm actually going to make an array in here called fibs. And I'll say something like, well, fibs.length right now should be 0. So I'm going to say while fibs.length is less than n, could be that it's n minus 1. I'll have to see. So this is 0. I want to get the 0th one. Yeah, I think it is going to be n minus 1. So 0 is going to get me, like it's currently 0, but what I'm going to do is each time I'm going to compute that first one. So while fibs.length is less than or equal to 1, I'm going to say fibs dot push. And I suppose I could also, just to make it kind of simpler to write it, maybe I'm not going to use fibs.length. I'll just use like a counter, and that counter will be equal to 0. So I'll say while the counter is strictly less than n, I think, I'm going to add stuff to push. What am I going to add to push? Well, I'm going to say something like, well, I'm actually going to start stuff with fibs. I'm going to say, okay, it's going to start with 0. Oh, sorry, it's going to start with 1 and 1 because fibs 0 is 1 and fibs 1 is 1. And so maybe that's actually in this counter or in this while loop, I want to say, well, maybe it's already in there. So if it's already in there, I'm done. And how would I know it's already in there? I say fibs.length, which would be 2 minus 1. That's going to give me if it's already in there. So yeah, I think I'm going back to saying while I take that out. Sorry, this is what programming in real time looks like. Okay, so I'm just gonna say while fibs dot, oh, sorry, it's not dot length, yeah, because I'm in Python. So while the length of fibs -1, so in this case, it's going to start out as 2, -1 is going to be 1. So if n was 1, it means it's already in there. So is 1 less than 1? No. So I think I want to say something while n is, yeah, is that correct? As in if n was 10, this would be 1. And because it's not the case, I want to get the next index, which is going to be len fibs.
I think it's just length of fibs is less than n.
Okay, let's try that. The off by 1 thing is always, can always be confusing, but what do I want to push here? I want to push the last 2 numbers. So I'm going to say something like, because it's Python, I could say fibs -1, which would be the last number. And this will be the second to last number. So here I'm saying just add the last number and the second to last number. And I'm already starting with 2 and push that on as the next thing. And let's just see this in action by me printing fibs each time. So I'm actually going to print fibs at each time. And then I suppose I could also add one to the call at each time. And then this should quit at the end. And I might have an off by 1 thing, but at the end of it, I just want to say, what's the last one? Return that. So let's actually call fib smart. And we're going to call it with the same input size. Okay, so now let me actually run this.
We need to do dot append instead of dot push.
Yeah, I'm always getting my languages confused. I find it hard to move between languages. And right, we need to do that global calls thing, just like we did here. Let's add it there. Okay, let's try that again. Okay, so in the first case, it took 177 calls. In the second case, you see how it grows over time. We keep adding 1 more based on the previous, which is how you would normally think about it. And then at the end of it, am I getting the right number? Looks like I'm off by 1 in some way. So fib naive 10, I believe, is the right answer, which is 89, but I'm getting 55 here just because I'm quitting early, I think. So this will change it a little, and I think I actually want less than or equal to n. No, that's enough now. Yeah, so the difference here, 177 calls versus 8 calls. And then if we see that again, so in this case, I could say like this first result, or it's really the number of calls I care about, but 177 versus 8. Well, let's double the input size now for both of them. Okay, so we're doubling the input size. And I should probably stop printing at this point because we know that it works. Okay, so the naive way, 170 calls, the smart way, 9 calls. So I doubled the input size, and this is the difference. Now I double the input size here. Look, it's insanely bad versus 19 calls. And this one here, the naive one, we actually saw that if I try and now compute it for, if I try and double it again for 40, what happens? Well, it actually gets caught. It can't do it because it's taking a very long time. It hasn't quit on me. It hasn't said Stack Overflow yet, but it's taking a very long time. So I'm going to kill it. And I'm going to take just that one out, but I will leave in the smart one. Well, the smart one, 39 calls. And based on how that is, I imagine, my limit now is not, 40. My limit is like 1 million. I mean, that number might be too big, but if I do this, okay, it's still going to take a while. That might be too big of a number, to be fair, because it has to create an array of approximately that size. I might want to cut that down a bit. Okay. Oops. Let me restart that. Is it not going to remember? There we go. So even for this really big number, I believe it will eventually finish. We're only doing fib smart here. I mean, it's a really big number. Might want to cut that down even more. Okay, so that's a gigantic number, obviously. But the fact is, we were able to, and did we know how many calls it took? In 99,999 calls. Okay, so that's an insanely large number, but we were still able to work with it because this algorithm is O of n. Because that list is going to grow. It's both O(n) space and time, because that list is going to grow as the Fibonacci number that we're looking for gets higher. But compared to the naive approach couldn't crack 40 without dying. Whereas this can go to 100,000. And that's kind of the big take home about complexity analysis stuff, that depending on, this is the same exact thing we're trying to solve, but depending on our algorithm, we either came up with something that, tops out real early and is very slow, or something that, could be reasonably more useful. Who knows why we want Fibonacci numbers, but if something had this sort of structure, if we do it one way, we can't have more than 30 elements seemingly and keep it working. Whereas in this case, we could have 100,000 elements. Well, a lot of problems are going to fit in that space. Okay, Noah, you say scroll up to what? Yeah, this should be in the curriculum. Basically, there's a bunch of things. I tried to improve the curriculum last week, but improving curriculum in real time can often be hard. This really should be there, but it just isn't there right now. But it is important to actually see this versus, I mean, this is technically what you're seeing right here. It's just, actually seeing the runtimes helps. That's part of what this big O demo thing is right here, where it's just actually showing you some algorithms and saying like, and then we'll see at the very end. So these are just sort of, classic versions of something that fulfills that time constraint. And then we have different input sizes that we run it against to actually see how long that takes. But if we go back here, I see it's 1017. One thing we do have here is just walking through examples. So let's just walk through some of these 3 examples, and then we'll take a break, and then we'll come back and we'll decide what to do with 2 things. So this is on all of you now. So if we walk through this example, let's actually try and we're going to walk through it on the right here and think about it on the left, which is just, text. So this example 1, what's going on here? As in, how might I start understanding this? Example 1. So I guess I can start us. It's sort of like, if I'm walking through this, I can actually look at each line basically. Just want to say it's text. Second. How do I say this is? Okay. So if I walk through this, I'm doing a bunch of things at each step. So this total equals 0. I'm just setting something to 0. If I want to be really explicit, I could say, okay, that counts as 1 operation. And then I move on to the next line, right? Well, the next line is a for loop. So because it's the next line, because I'm not nesting, that's like a plus. So we'll leave that one there for now. But now I have a for loop. What am I doing in the for loop? I'm saying for X in my list is a list, so that's our N. So this is now an N. And what am I doing for that N? Well, for each N, I'm multiplying a value by 2, and I'm setting it in value. Let's just say that's one operation. And then if value is greater than 20, so an if statement is not like a for loop, it just it's an operation that maybe runs, maybe doesn't. But if it's the case, so let's assume worst case scenario is the case, I'm actually going to enter in, and then I say for Y in my list. So this is like I did one operation, and then I did, this other operation, which itself, if I want to be really explicit, I could say that. So it's times what? Well, it's times N. And what am I doing for that N? For N times, I'm looking at this one thing. And if it's true, I do one thing. And then by the time this is all done, I have that return. So that's another +1. So if I want to be really explicit, I can multiply all this out, and I can say, okay, I'm doing one operation. And then after that, I'm doing N operations, and N times I'm doing at least one operation, but then I'm also doing, multiply that all out, I'm doing N operations. And then when that's all said and done, I finally do one operation. But based on what we know, we basically can just drop these ones because they're not going to matter for our big O. So we drop all the 1 pluses, and this just ends up being N squared. And the easy way to tell that is you look through it and you say, like, okay, I did something not related to N. I did something, oh, this is based on N and it's nested. So everything inside is going to be times. I did something not related to N. There's an if statement there, not related to N, but let's just assume it happens, because we want to see if that's the worst case. Okay, if it is the case, then that's N. That N is within another N, so that's N squared. And again, if something is true, then I do something, and then finally I return. But just seeing the doubly nested for loops, it's almost like in your mind, even though this wouldn't be the right algorithm anymore, it's like you can remove this. Doesn't really matter what it says in there. You can remove this, but you see there's a for loop within a for loop. You remove this. Okay, if it's a for loop within a for loop, that's N squared. Okay, so that's example 1. Let us together now, instead of me alone, do example 2. Yeah, so Eric, it would be ON squared. That's correct. So yeah, example 2. Let's start. For item in my list, what does that tell us?
It's just O of N, right? Because there's one loop.
We'll see. Let's build it up over time. As in, this is the whole thing. And now we're going to build it up over time. The first, like, we're calling this function. So the first line for item in my list.
N.
N, exactly. So we're looking at every item in my list. And then counter equals my list dot count. Well, this is actually confusing because I don't know how this works. But I'm going to guess, okay, to get the, what does this even mean? My list dot count.
You copied it over wrong. Counter, or wait, no, I guess that's just a 2-line breakup on that one. I don't know.
Yeah. Well, but I'm saying, like, my list is, I guess, a list. Does list have something on it called count? And it takes a certain number of items?
It counts how many times the item is in the list.
Understood. So my sense is this is going to have to walk through the whole list. If it's going to count the total number of items, like, let me just see that functionality. I open up Python and I say, list equals, to list of range 10. Okay, now I have a list like that. If I were to say list And let's just say we're gonna append a 1 at the end, so something appears twice. Okay, so if I say list.count and I pass that a 1, I get 2. The only way it can know that, as far as I know, it's not sorted or anything, it has to look at every element. So if it has to look at every element, even though we didn't write this, this is itself O of n. So we have a for loop, which is n, for every item in the list. We want to get the count of every item in the list like this. So that's a nested n. Okay. And then the next line, if counter is greater than 2, what do we do there?
That's just +1.
Yeah, well, because it's if counter is greater than 2, if it's false, there's nothing there. If it's true, well, it's whatever's inside. In this case, return true. So
You still have to calculate the conditional, right?
what was that?
You still have to calculate the conditional, right?
Yeah, as in, because we care about worst case, we say, okay, well, what if the counter is true? Or like, what if the conditional is true? Also, what if it's not true? We're just trying to figure out what is the worst case that can happen. And it looks like from this, the worst case would be that I give it a list. It looks through every item in the list. For every item it looks at, the count is not strictly greater than 2, so it never does this. And it just looks through the whole list, and it eventually returns false because nothing is greater than 2. Nothing has a count greater than 2.
But it always has to calculate the conditional though, right? So it has to calculate if counter is greater than 2.
Yeah, that is always happening, yes. But think of it in terms of like the input. So like in this case, my worst case would be something like this, where I have a list of length 5 or whatever it is. So it's like I'm going to look through each element here and I say, okay, for item 1, the count is going to be 2, and I'd have to look through the whole list to find that out. Is counter greater than 2? No, 2 is not greater than 2. This doesn't happen. For item 2, same deal. For item 3, 4. And so actually we look at every single element in this list, and for every single element in this list, we find out the count. And the conditional never saves us. It never, lets us short circuit, so to speak, and like end early. And then we eventually finish looking through everything on the list, and then we return false. So worst case scenario is we have 8 elements here. For each one of the 8 elements, we looked at all 8 elements to find out the total count, because naively, I'm just going to assume that's how that works. And so this would be n nested in n equal n squared.
I have kind of a dumb question. Like, why isn't it just n plus n? Since you're looking at everything twice.
Well, it's like this. If I just like make up an example, I guess I can do it in code here where you can like see it. If I say like def, I'll call it n after n, and it's arbitrary what I'm doing, but I'm taking in a list, and then I'll say like for elem in list print elem, and then after that I'm saying for elem in list print hello, or something like that. So this is a case of n plus n. I'm doing something n times, and then when I'm done, I'm doing something else n times. So we would say that's n plus n, which is 2n, but we drop the 2, so it's just n. Now, if we consider the alternative, n nested n would be like this. And what that's doing there is saying something like, okay, like, I guess if I have an example, in this case, I have a list like 1, 2, 3, 4. First, I walk through the list. I print 1, I print 2, I print 3, I print 4. Then I walk through the list again, and I print hello 4 times in a row. So for every element, I'm printing hello. And that's a total of 4 operations, n, plus 4 operations, n. But it's basically just going to grow 2n every time my n grows, and we don't care about the 2, we just say it grows by n. In this case, what happens? Well, I'm going to start with the same list. And what I'm saying here is for every element in here, so for the element 1, look at every other element. For 1, I'm going to look at 1, 2, 3, 4. And each time I'm going to print hello. So I'm going to print 4 times for 1. And now this loop is done. So I move to the next iteration of this loop. But now I'm looking at 2. And I print hello again 4 times. And then 3. And I print it 4 times. 4. I print it 4 times. So now instead of 8, it's 16. And it's n squared because for everything I'm doing with an element, I'm doing something with an element. It's a little weird to think about, but it's like I'm looking at 1, and then while I'm looking at 1, I look at 1, 2, 3, 4. Then I'm looking at 2, and while I look at 2, I'm looking at 1, 2, 3, 4. And so for every n, you're doing something n times. Does that help?
That makes sense. I was just thinking about the other problem, like in the wrong way.
Yeah, I mean, these examples are a little weird because they're so arbitrary. Like, I mean, let's just do this last one and then we'll be done. Looking at example 3 here. So we're starting example 3 takes in a list. So whatever we're taking in, that's our n. So it's like I'm going to say my list is equal to n. And then yummy list, well, yummy list always has a length 4. So I'll just write 4 there. And then I have something called food list. So what are we doing here for item in my list?
Whatever you're passing as a parameter is looping through that.
Yeah, so this my list that we pass in, that can grow. So for every item in there, so for n items, I guess I'll write it like this now. For n, what am I doing? Well, I'm checking if it's an instance.
In those things, right?
Hmm?
Yeah, so if instance, item, or string, so you have to check. Oh, never mind. Okay.
I'm honestly, again, a little confused. Is this saying if item is an instance of string? Okay, I guess that's it. We're just going to assume this is, we're going to assume this is constant time and this if happens. And then I think we've established that we assume dot append for a list is constant time. So
it's checking if it's a string, I think.
Yeah,
With that
exactly,
function.
yeah.
Evaluate and append, 2-step.
What was that?
So evaluate first, then append the item. That's 2 steps. Is that? Am I thinking of it right?
Yeah, exactly. So we could say like for each item, I'm doing one thing possibly, and for that one thing possibly, I'm doing one thing. So it's like for each item, I'm doing one thing. So I could say like for n, I'm doing one thing, or maybe I'm doing 2 things, but really that's just n. And so this n is done now. So that whole thing here was n. Okay, let's keep moving on. Yummy count equals 0. That's like 1. Shouldn't matter because it's on its own. And now I get here and I say for food in food list. What is food list? Well, food list potentially has every item from my list. So food list itself has size n. And then I say, so for n things, what do I do? Well, for n things, I say for yummy and yummy list. Well, yummy list can't change. So for n things, I'm going 4 things. Okay. And then if it's the case that food is in yummy list, then yummy count plus 1. So, for each one of these things, I'm just doing one thing, more or less. And then finally, I return. So I'm doing n things here. And then I'm doing n things here, but nested 4 things. So then it was like, if I do the total thing, it's sort of like 1 for that first line, and then I mean, it's not really even worth writing the ones for things like this and this because they're on their own line. They're not going to be the main thing. So for this ended up being n total. And then for this, it's n, but nested within it is only of size 4. So it's like we're saying n plus 4n. And then we return it. But that 4n, we don't really care because that yummy list could only ever be of length 4. And so we just drop that, and it's n plus n. And because we just want the bigger of the two, we just take 1. This one's just n. So I hope that helps a little. It is weird to do it in practice, but you're basically just trying to walk through in your head what is the part of it that can grow, which is usually going to be as input, and then how is the algorithm affected by the part that can grow. Okay, so yeah.
Sorry, if the yummy list didn't have a strict length of 4,
yeah,
it would instead be n squared because it's a nested for loop, right?
Exactly, yeah. So let's say it was like this. Let's say yummy list was passed in. We don't know the size of yummy list. It's also n. If we wanted to be really explicit, we might say it's size m. So we're kind of tracking them separately, but we really only care about the bigger of the two because that's going to affect worst case. So we'll just call them both n. And now if I say for this one, I'm only doing it n times, but for this one, I'm saying for every food item in the food list, that's n. Nested for every item in the yummy list, that's also n. Now it's n squared. So whenever you're nesting a list, even if it's the same list, and that list could be arbitrarily sized, you don't know the size, then that's a multiplication operation on the ends. Yeah, what Eric Bowman wrote in the chat is correct, I think, for this one. If you want to be explicit about it, you can say like, okay, this counts as, I guess I'll write it on the left, like this counts as like O1. So that itself is an order 1 operation. This is an ON operation. Inside of it, we'll just say that if statement happens, it's an O1. Inside of that is an O1, another O1. In the case of what we're working with right now, that's an O of N. That's an O of N. That's an O of 1. That's an O of 1. That's an O of 1. And then if I wrote it out, I put the O on the outside, and then I say, okay, 1. And then because it's a separate thing, N times 1 times 1. And then plus 1 plus N times 1 times 1 plus 1. And then when that collapses, that's going to turn into just N for this, just N squared for this. Rogelio, I see you. It's intense. Okay, and then you just drop the 1s. And now you drop the 1s, but you're like, well, which one's bigger, n squared or n? Because there's a plus. Okay, it's n squared, and we're done. Because it does one thing, it's O of n. But even if it did 2 things or 3 things, it doesn't matter. It's just the case, like, because you saw when you add a bunch of 1s together, turns into 3. Well, you drop that factor. It's just 1. So like, for all I know, it takes a few, maybe like in reality, it creates the food list, spot in memory. And then as a second operation, it puts the empty array in there. So if it's 2 operations still, the idea is it's not related to any kind of input size. If it's not related to any kind of input size, it's O1. But yeah, this can be tricky because at the end of the day, it is math. And the way we do it is just kind of a shorthand because we don't want to do the math, but that's what it is. Okay, I want to give you guys a break. Let's get another, 10-minute break in there. Be nice to have a break. We're going to come back at what is 10 or 11:50, which means we have 10 minutes. And as you can see, there's a little more stuff here. Like there's this hash table thing. I wanted to include it, but it's it's too much to get into. This was just part of day 1, so I moved it to day 3. But a hash table is just an like a dictionary, and it's good maybe on some level to know how it works. But the take home is that you're able to get this constant time lookup. Now we have some problems for today. But what I want to do when we come back for the last 10 minutes is talk about sorting a little bit. So you have a 10-minute break starting now. Let's come back at 11:50 CST.
Hey Ben, I was also wondering, you know how so Python has those built-in functions, such as like sort and sorted,
Mhm.
and those functions only exist because uh, we do that operation so many times, they make it built in eventually. But they're running like for loops in the background, right? So how do we actually see that method like break down? Like I was trying to Google like one of them and I can't find how it's like broken down.
Yeah. So the reality is that when you're using a programming language, you don't know for sure exactly how it's implemented. I'm not sure if it's going to be easy for me to actually see the implementation anywhere. It's the kind of thing you can Google. What we're trying to find out is Python sort complexity, and you can just kind of you have a somewhat guarantee that it's going to be as good as it can be because they're a professional language. But you didn't write it yourself. But part of that is just oh, and this they're talking about Java right here, I think. I'm not sure. But yeah, there's without digging in deeply, you don't know exactly what algorithm they used or what it's doing. But you could just accept that for certain things, you just have this like, you just can accept that is what it is. That if the best case for sorting is going to be O n log n, they're using one of those algorithms. And then if it really matters, you can like dig in and find out exactly how they implement it. Because, eventually these decisions do get made. There's like the PEP or whatever, like the Python. Is that what it's called? PEP, Python. Like there's like right, exactly. So Python actually tracks everything they do. So somewhere I could find out about their sorting algorithm and exactly how it works. But I'm not sure where I would find that. Okay. I guess
Yeah, I didn't know if it was like a VS Code thing. If you remember when Francisco like clicked on like I don't know if it was like a method, like a keyword in the syntax that led him to another page.
Yeah, I can try that. So right, if I click on like append there, like I did like alt click because I think I have my IntelliSense stuff well hooked up. So it's going to bring me to something internal in Python. I'm not sure if I can see the actual. I could look for like sort here. This is kind of telling me like what sort expects me to take and stuff. It's not necessarily showing me the implementation. Not sure how I would get to that. Because if something is so basic to a language that it's built in, you end up in this situation where like, well, Python, the actual Python program is written in C. And so the implementation for list.sort is more than likely written in C. And so you don't necessarily see it in Python or can analyze it, but yeah, I mean, it's this is why it actually like in practice, actually finding out the complexity for a real thing as opposed to just like an algorithm that you're thinking about in the abstract can be very difficult.
Gotcha. Thank you.
Yeah, and when we come back, I think we're going to do this hash table thing because it was the next thing anyways. was a lot here.
You are still recording.
Yeah, I know. I'm just building what
Okay.
to do in a second. This is how the sausage gets made.
For a while loop, every time I loop through the while loop, is that another uh n times n?
Um, every time you loop through the while loop, is that another n times?
Like,
yeah, I mean, if it's nested, yes. Well,
okay.
no, I mean, it really depends what your while loop is. So it can get confusing once you're using recursion or a while loop. But basically, are you worst case scenario looking at all the elements? And then if you're nesting, for every element you look at, how many elements are you looking at?
Okay.
Yep. So imagine we're coming back in a minute or two, right? Let's wait for some bases to show up. Okay, I think people are back. It's 10 or 11:50 CST. So the last thing we're going to do is talk about this hash table thing. This is part of the reason why doing data structures in a week is very hard, because this can be like a 2-week project, but it's not. We're trying to understand how a dictionary actually works and why it's able to get this constant time access, constant time lookup. So this is a definition of a hash table, and I'm going to like draw it out over here. And in this case, we're using, so we're making this internal thing called self.table, and it's a list, but the list itself holds a list of, it holds 64 empty lists. So 64 is too big to draw. I'm just going to use 4, but the idea is the same. So each one of these lists, each one of these array elements holds an empty array itself. And the way that actually works would look like this. So initially they're pointing to nothing, but the idea is each one of these, I have 4 elements and they're indexable, and each one is currently pointing to nothing. And then the first thing we have here is this hash function. So the reason why a dictionary, the data structure it's based on is called a hash table is because of this idea called hashing. And hashing is a concept you'll see throughout computer science, but basically it means that you're going to use, you're going to convert some value into another value for the sake of converting it into like an indexable number. So this might be easier seen in terms of like down here. So underscore hash underscore, because it's private, it's actually going to be called here. So we see like in set, we have index equals self dot underscore hash key. What's the key? Well, we see here, like in, we created this hash table and we're saying set name to Alice. Name is the key. So what it actually runs here is self dot underscore hash name. And name is the key in this hash thing. So we can actually, look at this in Python, what actually happens here. Okay. So I'm saying like hash equals 0 by default. And then I'm saying for character in the key, I'm asking ordinal for the character. So the key in this case is name. So I'm going to say something like key equals name. Key equals name rather. Okay, we have a key there. And then at some point I'm looking through each character in it. So I just want to see what that looks like. If I say ordinal of K, or sorry, of N, which would be my first letter, what is that? That's 110. So basically letters can be converted to numbers because letters are ultimately represented in ASCII, and that's just a binary, which is a number. So what we're doing here is we keep adding all the letters together to create this hash. So let's actually run that. We'll say for car in key, my key is name. What am I going to do? Well, I'm actually going to take that hash, which currently equals 0, and I'll add to it ord of car. I run that. And what happens at the end? Well, I look at hash now and it's 417. So that's a unique number that represents adding all the letters together. But 417 is way bigger than the index of our table here. So what we do is we say 417 hash, and we mod it by the length of our table, which in this case would be 64. So in this case, I mod it by 64 and I get the index 33. But for instance, on my little local Excalidraw thing, I only have 4 here. So I got the index 1. So this hashing function is just a way to convert the key, which is a string, to some kind of number, and then use modulus to uniquely get an index for that number. So in this way, we're always able to associate a key with a specific index. So let's say I'm looking at this for my hash table. I did name. It turns out name after doing the hash and then dividing it by the length got me the index 1, right? So here my index now is 1, and then I say self.table, which is, this entire table. I get index 1, and then I append to it. Well, this is wrong here. I shouldn't be appending to it both a list of the key and the value. I'm really just appending to it the value, because it's all about key to value lookup. So the value there was what? Name to Alice. So we can just imagine this fits in one box. I'm going to say Alice. We'll make it much smaller. Okay. So now let's do another one. Age, right? So I'm going to do that whole thing again, where I'm going to say, okay, hash is equal to 0. And then I want to set the key to age. And then I'm going to say for character and key, I want to do hash plus equals ordinal of the character. So now that that's done, I look at my hash and it's 301. But I'm going to take that hash and I'm going to mod it by the length of, if it was 64, that would be index 45. But because I only have 4 in mine, I get 1 again. Okay, so this is actually a pretty good point. So I got 1 again. So what do? I look at here, I say, okay, index 1, go to index 1, append something else to it. So I actually have, index 1 points here. The first thing is Alex. The second thing is now 34. And I'll just keep following this example because this one's collisions are different than mine, but what just happened is called a collision. So because we have a limited amount of space in our hash table, we can't, sometimes these keys are going to match to the same thing. So in that case, now I say my hash dot set main. So let's do that all again. So can you clear the screen? Is that a thing? No, it's not. I'll just go like that a bunch. No, that doesn't help either. Okay, so I'm just going to go back and I'm going to grab hash is 0, and then I'll say key is, in this case, main. Which, and that's a good point. Main and name should have the same hash, right? Because it's the same letters, and based on how we wrote our hashing algorithm, that's going to have a collision. So, I mean, honestly, I'm going to use a different example. I'm going to just make a random key because I want to see us not having a collision. So in this case, my key is going to be AB. It's a little easier to have collisions too, the smaller it is, the smaller the table actually is. And now I'm going to do that again, the thing where I say like, okay, well, for each character in the key, do that. And now when I look at my hash, it's 195. And I'm going to mod that by 4. And now I got a 3. Okay, so I'm going to put the word, my key was AB. And I guess I'm putting the word luxurious in there at 3. So now this is going to be just lux. But that's how set works. So set is going to use that hash function, convert the hash function, convert the key that you passed into set into some index that it knows about at this top level. And that's how it gets the main thing. And then it adds to this list it points to. And if it has a collision, meaning if multiple keys point to the same thing, which will definitely happen when it's this small, then you just add to the next thing. And now let's see how get works. So get, I imagine, is going to similarly use the key. It's not very different than set. You're just not setting at the end of the day. So now I'm going to say, okay, get self key, right? So the first thing is I take the hash. So in the case of name, I already know that that's going to match based on the hash to 1. So the hash is not really random. It's just that it associates, you know, a string with a specific indexable number, but it's going to be the same every time. So given that key name, we know it matches to 1. And now I'm going to look through, yeah, I guess this is why they wanted to save the actual key there, because in the case of a collision, you want to know which one you're talking about. So in reality, I would want to know not just the word Alice there, but also that my key was name. And same with 34 here, I would want to know that that key was age and the value was 34. And then for Lux in this case, I guess we ended up saying AB was the key. So now it's going to walk through here and say, okay, I've narrowed it down to things that match this hash. Now, which one is it? And it's going to look through it. And if name is the right key, then it will return the value Alice. So that's all there is to a hash table. I don't know that this was necessarily useful because it's not so easy to see why it gives you the guarantee it gives you. But you're given this guarantee that it's essentially constant time. So because of this hashing thing, if that hash is really large, what it means is that most of the time I have a key value pair, it's going to be matching to, you know, a different index. And so it's not going to have to look through too many things to find it. If there's a collision, it will, you know, it will have to look through perhaps multiple things. But the way the math works out is that collisions are going to be rare enough that you still can get what's called, you still can get constant time access. I see there are a lot of comments and I can look at them now. You are technically off now, so it's 12:02 CST. You guys are free to get lunch anytime it is 12 noon CST. Assuming that's the schedule, you're free at that point. So if you have to go somewhere, by all means, go somewhere. When we come back, I believe we're pairing today, and then we're going to work on the assignments that are at the end of the curriculum doc today. But yeah, I mean, I can stick around a little to read through this chat and discuss it. But yeah, any questions before we leave? The hashing stuff is not super necessary. It's not related to any of the assignments today. It was just something to cover while we had a little time.
So what's the default bit size for the Python dictionaries? The
That's a good
64 or
question.
32?
What was that?
Is it the 32 or 64?
Yeah, it's a good question. I'm not actually sure. Like, that's one of those like implementation details. So if I say like Python dictionary default size, I might be able to find it. Not sure that I would be able to find it. These tend to be like implementation based details, and you're just supposed to trust that Python has done the math to figure out what good sizes are, and if they ever need to resize it, they do resize it. The essential thing is just that you have this, we call these like buckets. So the hashing algorithm is going to make it so you narrow down where you're putting something or where you're looking to get it from into a bucket. And so if I have 64 buckets, chances are, even if I add, you know, a bunch of elements, like if I add 128 elements and it's perfectly balanced, that means for any given lookup, I'm doing, you know, one operation for the hash, and I have to look at two unique things to see which one is the right one. But I was able to have, you know, a 64-bit hash table and, or sorry, a 64 bucket big hash table and add 128 elements, and I only have to look at two things. Whereas if this was some kind of, you know, array or linked list like thing, I would theoretically have to look at everything.
Yeah.
Yeah. I'm not sure to what degree that is super helpful at this point. even discussing hash tables in general. But yeah, this is a.
And are you able to demonstrate what Bennett replied to me?
Say that again?
I'm not understanding how the hash table's working.
Yeah.
Bennett replied to me saying if the ASCII value is 4 or higher, that index doesn't exist in the hash table, but by doing the mod as the size of the table, you always get a valid index into the table.
Exactly. So you're asking why that.
I'm asking you if you could demonstrate, because you say exactly. I don't understand it.
Yeah, well, no, that's what we were doing here. So like, if I have a key equal to name or age, right? My age is key. Well, based on how that hash thing was written, we walk through, oh, and I should set hash back to 0. Well, I'm actually going to walk through every character in the key. So I'm going to walk through A, G, and E. And what I'm going to do is I'm going to add that to this variable hash based on turning that character into a number. And that's not that's one way of doing hashing. It's not the only way, but at the end of the day, I used age and E to create a unique number 301. So age and 301 are the same thing.
Right.
I pass around age and it knows, okay, 301. But I don't have an index 301 in my hash table, right? Well, if my hash table had 64 slots, like the one in the code, okay, mod is going to give me a number between 0 and 63 related to 301. So in this case, it gives me 45. So is that the part you are concerned about?
Yeah. So what does the 45? The 45 is the index, or
45 is now the index that we care about. Yeah. So
okay.
The way the way mod works is that mod is going to tell us like for any number we give it, it's going to tell us if I divided this by 64, what would be the remainder? So because of the nature of that operation, if I gave it 0, it would give me 0. If I gave it 1, it would give me 1. If I gave it 63, it would give me 63. If I give it 64, it now gives me 0 again, because the remainder of 64 divided by 64 is 0. And if I gave it 65, it would give me 1, because 65 divided by 64 is equal to 1, but the remainder is 1. So modding something by 64 guarantees that we'll get a number between 0 and that number, non-inclusive. So 0 up until but not including 64, which is perfect for indexing.
Gotcha. Okay, that makes more sense. Yeah.
Yeah, and the main thing is just that because of the way this algorithm works, I now have this guarantee that I don't need to remember 45. The word the word age, the key age, always maps in my hash table to the number 45. So the key is enough to figure out which bucket I care about.
And that bucket is an element in the list of the list, right?
Yeah, so in this case, I only have 4 of them here, but it would be the same thing where if I had 64, it's just a matter of which one it maps to. And whichever one it maps to, you add it there. But the concession is that there might already be something there. Because if you keep adding things to this dictionary, there might already be something in the bucket 1. So in that case, we add something, after it. And for all we know, that's like, not implemented as an array, but a linked list. I'll get my arrows, but it doesn't really matter, because what you're going to do is you're going to store both the key and the value. And so the bucket is a way to quickly narrow you down to things that, only fit that bucket. That key uniquely fits that bucket. There's lots of things in other buckets, but you don't care about those, because if you're looking for something with a key age matches to this bucket. If it's been added, it's already in here. If it's not been added, it's not in here. And so what the hashing does is it it narrows down your search space to just the bucket that matches that key. And then you might have to go through one at a time and say, well, is it like, I see there's something called name in there. Is it name? No, that's not my key. I see that even though it has the same hash, is there something called age in there? Oh yeah, age and age match. Okay, return its value 34. But let's say I was looking for main, right? MANE. Well, that should match because that has the same letters as name. That should match the same exact bucket. But when I would look for it, I would say, okay, main, like get main. Okay, well, I match to 1. Then I look at name. Name is not main. Age is not main. End of list.
Makes a new one.
Main's not in there. What?
Oh, I was thinking it makes a new one. It puts it under age.
Yeah, and it would for set. But like, let's say I was trying to get something that wasn't in there. It would still match to 1. And then it would look and see, okay, well, it's not the first one. It's not the second one. If I was setting it, I would have the key and the value, and I would say, okay, it matches here. Maybe I would want to, if I wanted to make sure I overwrote stuff, I would say, okay, well, look if it's already in there. If it is, overwrite it. If not, add it to the end.
So it's the same concept of like the binary search where like you're cutting because you're assigning things to this bucket, you're cutting your search query all the way down to like one specific spot where like same in binary, you're like, all right, we don't need the right side. We can just look at the left. Okay.
Yeah. So the hash table thing can get more complicated because of this idea of collisions. Because that's not really a concept with like binary search, but in the same way, because of the hashing function, if I start out with 64 buckets, at the very least in one move, I'm narrowing it down to 1 bucket. And then if there's other stuff in that bucket, I might have to look through that other stuff first. But it's useful because it's sort of like, let's say you had it's kind of like the idea of a Rolodex in a way, where it's like, let's say you had a Rolodex and it had names, categorized by the first letter of the last name. But they weren't necessarily all in order. They were just categorized by first letter of the last name. So the fact that someone has the last name Cannon, I'm able to eliminate 25 of the slots because I know your last name starts with C. That there's only 1 bucket for that. So I jump to the bucket C. Maybe I have like 5 names in there, but just the fact that I was able to jump to C is really useful. Now I only have to look through those 5. Maybe one of them already has Cannon in there, and so I update it. Maybe Cannon's not in there, so I add it. And I might have to look at all 5 of the things in there, but on average, I'm saving a lot of time by cutting.
You're looking at 5 instead of like 80 or whatever.
Exactly. And the alternative to something like a hash table would be, well, let's say you didn't have an ordering at all. You just had all of your contacts in a single list. Well, then you would have to just look through it one by one because Cannon could be in the beginning, Cannon could be at the end. So a hash table fundamentally is this idea that, like, just like a binary list, there's this concept of there is some ordering. There's some implicit ordering. So let's take advantage of that.
Right.
And that's why Python calls them dictionaries, because that is what a dictionary is. Like, you jump to D. I mean, technically it's all in order, but you're able to easily jump to D. And then you could say, oh, dog. And like, yeah.
All right. Thank you.
Yep, no problem.
And this method of resolving a hash collision is called what's it called again? Because there's another one that it's like called open addressing, I think, where it like goes down and finds the next open address.
Yeah, I mean, there's definitely different strategies. I'm not sure that I know that one specifically. When I don't even know what I would call this strategy. But the basic idea is that you have these buckets, and then you have the buckets point, like there's a limited number of buckets, but the buckets point to something that can keep growing, like a linked list. And so you keep adding things. And if you're unlucky, everything's going to map to exactly 1 bucket. You're just going to keep adding things. They're all mapping to the 1 bucket. You are not really saving any time compared to a linked list. But on average, you're going to have a much better case scenario that is provably constant time. I'm not sure about the open addressing thing. Yeah, okay, so this is called chaining and something else is called open addressing. Okay, is that it, Rogelio?
I'm sorry?
You asked the question just now, right?
I did not know.
Oh, who asked the question?
That was me. That was Eric.
That's very funny. It's still highlighting Rogelio's name as if he spoke. Like his box is highlighted in green. It's Zoom is so weird.
Flying under the radar.
I guess, yeah, I don't know. But yeah, okay, well, that is the answer to your question, Eric, is I don't really know about open addressing, but I guess this is called chaining. And yeah, it's kind of like there's so many possible solutions to these problems. Like even to this day, you could still get a PhD in data structures. There's data structures out there that people haven't thought of, or just that are useful for specific cases, slight optimizations for specific cases. Yeah, anything else, or should I leave and upload this? Because Zoom does not download stuff until you leave. Okay, stopping sharing. Get out of here. Okay, cool. I am going to leave now. Yeah, and I believe we're going to be sending out pairs this afternoon, and you're coming back. I should have said that first, but you're coming back when the schedule says you're coming back, which is the normal time for coming back, which is 1:30 CST. Cool. Take care, everybody. And are there any TAs here to assign as the host? No, so because Eric was the last to speak, Eric is now the host. Great power, great responsibility.